what we argued in the yesterday lecture is that Condorcet winner is the top choice of the median voter. Right? So if we want to make C2 the winner, so we have to make C2 the choice of the median voter. Right? So we don't get to shift voters, but we get to erase voters. So we have to make sure that this guy who is ranking C2 first is our median voter. Well, there are 3 guys before C2, here 3 guys to the left. So we have to erase voters so that there are at most 2 guys to the right of C2. Right? So that means that we have to erase these 2 guys. Right? So that's all there is to it. So we figure out who should be made the median voter and erase voters on one side of him. Okay, so for single crossing, is it really different for single crossing? Yes. And the median voter, again, so the same thing. So you find a voter who ranks your preferred candidate first. You want to make one such voter, there may be several median voters. Right? So the only slightly subtle point is there may be several of these guys. So you have to decide from which side of your electorate to delete voters, either from the left or from the right. Right? But yeah, that's basically the answer. Right? So again, so the main point is, so you want your preferred candidate to be the top candidate of median voter, so you have to make a certain candidate the median voter. Right? So this is problem number 1. Okay, so problem number 2, so we want to prove that kind of distances in the single crossing profile behave in this kind of nice additive way. So if I have a vote x here, so this is my x, this is my y, this is my z, and the profile is single crossing. So every pair of candidates crosses at most once, right? Then I have this equality. Sorry, say it again.
There are 3 primary statements here. First is the swap of, so if we talk in terms of sets, then swap of xy is a subset of swap of xz.
Okay, yes, so we are, okay. So I don't remember if we introduced a notation for that recently, but let's write it as swap. Swap xy is a subset of swap xz. Right? And similarly, we have swap yz is a subset of swap xz. Right. Okay. All right. Okay, yeah. So now what we have from that, from the sizes of these sets, okay, so from this we have sort of weak triangle inequality, if you like, right? So the distance from x to y plus distance from y to z can potentially be, is at least as large as xz, right? So I think this is what we have. So what remains to prove is that these swaps and these swaps are disjoint, right? So this is what we still need to prove. So why is that? So swap xy intersect swap yz is an empty set. So why is that? Because single crossing property, exactly. So if some pair contributes to swap xy, so it's a pair AB, so it contributes like that, then that same pair cannot contribute to the distance between y and z, because it has been swapped already, so if we swap it again, it will be double crossing. So no pair can contribute both to this and to that, right? And therefore, these sets are disjoint, right? And therefore, we have the exact equality. Okay, very good. So now that we are done with the second problem, so we have the third problem, right? So if all votes are distinct, then up to reversal, there is at most one single crossing order of voters. exactly.
And then from one of them, if we just order by distance, all of them.
Right. Yes, exactly. That's exactly the solution. So let me rephrase it sort of slightly more slowly. So what we argued yesterday in the lecture in our recognition algorithm is once you guess the first voter, then from that voter you order by distance. Right? So you order by distance uniquely. There is no choice. So in a way, so what we already proved that kind of for a given first voter there is just one ordering. But there potentially could be several first voters. So how do we deal with that? And this is where this observation comes in. From this, we know that the maximum distance achieved in the single crossing profile is between the first voter and the last voter. So if we look at all pairwise distances between votes in our profile, there will be exactly one maximum distance, and the two guys for whom this maximum distance is accomplished is exactly the first guy and the last guy. So we actually don't have to guess who is first and who is last, but we can take, well, whichever one of these two guys that implement the maximum distance. Right, so they're actually given to us, and from then it's unique. Okay, so that's one proof. There's a bunch of alternative proofs. So I'm not sure. I think you have an alternative proof in a paper of yours, or maybe it's this proof. Right, so there are several proofs. So it's a nice statement. I think it has been rediscovered by several authors independently, right? But it's actually a nice and useful observation. Okay, so we are done with this page of exercises. So we are doing well time-wise. Okay, but I have more, and Neil has more if we need. Okay, so a couple more. Okay, so I'll let you read that and kind of tell me what you think. Okay, so I want to argue that if I have a single crossing profile, then it looks like that. That in particular, so it cannot look like this. So I cannot have a vote that ranks B first before a vote that ranks A first. That this is a bad situation. Why? Sorry? Yeah? By definition, yes. Okay, right, so if this guy ranks B first, right, then he ranks A somewhere below, right? If this guy ranks A first, he ranks B somewhere below, right? And these are kind of my undesirable double crossing, right? So this cannot be. This is an extremely useful, so this was very easy to prove. This is actually an extremely useful statement because it tells you that if you look at the first vote, right, it actually tells you how those candidates are going to appear at the top. Right, so at the top, the candidates are going to appear in blocks. So if the first guy is here is C, so first you have a block of votes that rank C first, then you have a block of votes that rank A first, then a block of votes that rank B first. Right, so kind of you take this first vote, and it actually, then you sort of turn it 90 degrees, and it tells you what's happening there. Right, so it's a simple fact, but it will be it's a useful lemma for many algorithms that work with single crossing preferences. Okay. Right. Okay, so what I mean is this. So suppose this vote goes C1, C2, CK. Right? Then if I look at the tops of these votes, right? So first I have votes that rank C1 first, then I have votes that rank C2 first, etc. Right? So in a way, the top row looks exactly the same way as top column, except possibly with duplications. So for instance, this turns out to be very useful when you design algorithms for multi-winner voting with single crossing preferences, because it tells you that things come in blocks. Okay, so a related problem is this. Right, and this is a very nice relationship between single peaked and single crossing, which actually looks surprising before you start thinking about, but it's not very difficult to prove. So if you have a single crossing profile where each candidate appears first at least once, then it's single peaked. So here's a hint. So it's difficult to prove that something is single peaked if you haven't fixed an axis. So it's easier to guess an axis and prove that it's single-peaked with respect to that axis. And this is the axis, right? So it's a related problem. Okay, so let's try to argue that this works. Right, so suppose, okay, so let me now give them coherent names. Right, so suppose here they appear as C1 up to Cm, and therefore we know that kind of here they appear, so a bunch of C1s, then a bunch of C2s, then a bunch of Cms. Okay, and I already have an axis here, so I just have to erase that. Right, so this is going to be my axis. So it's single crossing. Everyone is ranked first at least once. So I have to take a vote here and prove that it is single peaked. Okay, so this is my axis. So how I'm going to prove that? So the first vote is fine. The first vote is certainly single peaked with respect to that axis. Right, so now, so let's see, which definition of single peakedness do we want to use? So maybe the prefix based. So contiguous segments. So each prefix is contiguous. Okay, so how would the argument go? Mm-hmm. Mm-hmm. Okay. Mm-hmm. Right. Okay, so let me see if I can rephrase it in a useful manner. Or maybe, okay, so actually just so that it's recorded, right? So how about you go in front of the whiteboard, right, and explain it to the class?
I'm not too sure if that's the correct idea.
I think that works.
So we've proven by the last exercise that this will, the order will be, it won't change. The C1 can only be at the bottom of C2 of this preference. If let's say this is C2, so and everything below it will still, because it's single crossing, let's say it was in lexicographical order, so it would still be in lexicographical order with C1 at the end. And then we would have a peak for C2 first, and then C2, C3, you would form contiguous bands segments here, and C1 would come at the end. So
let's see. So I don't think it's necessarily true that C1 comes last, right? So what we can have is C1 coming second here. So C2, C1, C3, Cm. Right, so we just swapped C1 with C2 once, right? So this is still, right? So this is still legitimately single crossing, right? But again, but on the other hand, it's still kind of satisfies this property, right? So it's still single peaked. So it's not really counterexample. It just shows that single crossing profiles are a little bit more diverse than you thought they would be. But still, okay. So if you look at this vote, right? So this vote is, okay, so this vote is starting with C2, right? And kind of, so C1 shifted below C2 and possibly further, right? So here now in this vote we have C2 above C3, right? And this vote starts with C2, so it's still above C3. Okay, so what can we conclude? So let me give you a little bit more time to think about it maybe. Yeah, so it's the vote of the first voter, and because the profile is what is called narcissistic, and every candidate is ranked first at least once, from what we argued, this is also the order of appearances of candidates on the top. Okay, yeah, so let's try to do that. So let's try to argue from contradiction. So let me maybe put it back. Okay, so the argument is that if there is a valley, right, so, or in other words, if some top segment is not contiguous, so we reach a contradiction. So let's take some vote here, right? So let's say it starts, so it's not necessarily C2, it starts with CI. Right, so there's some vote here, starts with CI, and there's a valley. So this is voter, so let's give him a name. So this is a voter V. And in the preferences of the voter V, there's a valley. Right, so voter V ranks. So voter V's preference goes like this. Okay, so what goes wrong?
So, so let's say the points of the value are, say, ABC for the
Okay, so let's give them names. So these guys are, okay, so CI maybe, okay, so no, I was this guy. Okay, so let's erase that. So this is voter V. There's a value in his preference that goes as CI, CJ, CK.
So then that means for voter B, the preferences would be something like CI, CK, and then below that CJ.
Okay, so CI somewhere, then CK somewhere, CJ even further below.
Let's call the top choice of voter B as CV. Let's call the
Right, so there's also something on top, which may be CI but may not be. So this is CV, yeah.
So now the argument is that we know in this ordering of the voters,
Mm-hmm.
we know that CI as the top choice occurs, the voters with CI as the top choice occur before voters with CJ as their top choice, and after that comes the voters with CK as their top choice, right?
Right,
So
okay.
now the point is that if this is true, then J and K have already have like crossed
Mhm.
over before.
Right.
So then, and now CJ, voters with CJ as their top choice would come after this, voters with CK after
Mhm.
top choice would come after this, and then then we reach a double crossover.
Right. Okay, so let me just repeat that for the microphones. I believe what you say is exactly true, so let me just repeat it for the microphone. So we may have some cases to consider based on how I, J, and K relate to V, right? So that makes things slightly annoying, but let's kind of assume the simple case. Okay, so what can we assume? So here we have these guys. So let's look at the first voter. In the very first vote, they certainly appear in the proper order. So CI, CJ, CK. Right, so we can look at the first voter, right? So to make our life easy. Right, so first voter goes like this, IJK. This voter goes IKJ. So J and K, from between here and here, J and K have crossed. Okay, so now let's see what happens at the top. Right, so CI, okay, so CI is ranked on top before CJ. So here I, okay, so here I is above J, so here I is still above J, right? So the vote that ranks CI first comes before the vote that ranks CJ first, right? So otherwise there's a crossing, right? So this means that we still haven't reached, okay, so the vote that ranks CJ first comes after that, right? So there has to be a vote that ranks CJ first, and it has to come after this point, right? Because if it comes early, if it comes before that, this JI vote, it will be a double crossing between I and J, right? Because we have IJ here, this vote cannot be in between. So it has to be later, right? So this vote JI comes later. Okay, so now what can we say about, so now I think we have to look at CK, right? So that's, right, so here we have JK, here we have KJ, and here, well, somewhere we have CK. Above or below CI, I don't care. But one way or other, it's double crossing. Okay, yeah, so that's the argument. Okay, so therefore this profile is single peaked. So single peaked and single crossing is related, right? Okay, so this is a simple fact. Right, so it was, I think, first observed by Salvador Barbera and somewhere else in the 80s. So it's sort of based on this simple fact, you can basically get something very similar to a characterization of single-peaked, single-crossing domain. So which elections are both single-peaked and single-crossing. Okay, so this tells you that if a single-crossing profile additionally has this mild restriction of having every candidate on top at least once, right, then it's single-peaked. So this restriction is known under the name of narcissistic. So coming from the Greek or Latin word, one of those, kind of narcissistic, meaning caring about yourself. Right? And the idea is that candidates themselves, if they also participate in the elections, are likely to, at least vote for themselves. Right? So if you have this property that candidates actually participate in the election, so you're going to have this. Right? So if your profile is single-crossing, then it's also single-peaked. Right? So it's not quite a complete characterization of when a single-crossing profile is single-peaked. So a single-crossing profile may be single-peaked without that property, without having each candidate ranked first once, but it's sort of close. Right? So it should be able to extend your profile to having each candidate appear first at least once, and that's exactly when it's single-peaked. Right? So that's the story there. Okay, so we are done with this slide. So K candidates away. I think so, yes. Yes, I think that works. Right. Okay, so now to change gears a little bit. Okay. So now we have elicitation problems. So I have two on this slide, and I think we have time, so I think I'll get Neil to talk about. So I'm asking here about single-peaked and Euclidean, and I'll get Neil to talk about single-crossing version of that, because that's actually her work. Okay, so here's the question. So suppose you somehow know that so you have a voter, you have an axis. You know that those voters' preferences are single-peaked with respect to that axis, right? Because we're asking the voter to express preferences over water temperature in the sea, right? But you know what the actual preferences are, and you want to elicit them fully. Right, so now in general, if you don't know that preferences are single-peaked with respect to some axis, you're trying to elicit one of m factorial possible preference orderings. So worst case, you need m times log m comparisons. So this is like classic lower bound for sorting. Right, so if you're trying to get a full preference order, you need to ask m log m questions. Right, so my claim is that you can actually do better if you know that your profile is single-peaked with respect to a given axis. So, okay, so but tell me what the best you can do. Okay, so I'm asking this here about the profile, but obviously, so profile consists of votes, and those votes are independent, right? So this is actually meaningful as a question about a single vote. So you're just trying to elicit a single vote that is single-peaked for a profile. We do know the axis, yes. So this is your axis, and you know it. So you just don't know how the vote shapes up with respect to that axis. Right, so you can do m log m. So the question is whether you can do better. So m log m would be just basically trying to sort an unknown order to the right order or whatever. Right, so we want to beat m log m. Right, so one obvious target would be linear. Okay, so how you do that? So how do you get the peak? How do? Okay, so maybe I didn't explain the model properly, right? So let me be more explicit about that. The model is you have your voter who sits in front of you, and you ask him questions. How do you compare A and B? Which of the two you prefer? Right. So you don't get to ask him what is your peak. Right. So you'd have to get there. You could, and that's one way of doing it in linear time, right? So okay. So but yeah. So if someone wants to pursue this idea, that would also lead to a linear time algorithm. So. Sorry? Okay, but so that's still linear, right? Kind of order of m. so let me sort of formalize this idea. Okay, so first you want to figure out the voter's peak. So how do you do that? That's effectively looking for a maximum in an array of m numbers, right? So you ask him about two arbitrary candidates. Do you prefer A to B? He says B. Okay, so B is your current leader. You ask him, do you prefer B to C? He says B. Okay, now you know B is preferred to A and C. So you compare the current leader to whatever is left, right? And you find the peak. You find his top choice. Okay, so you found his top choice, right? So once, and that took you m-1 query, right? So it's exactly m-1, worst case, best case, irrespective, right? So now you know that from there, his next candidate, so if this is Cj, his next guy is Cj minus 1 or Cj plus 1, right? So you have to ask him just whom he likes better, J minus 1 or J plus 1. Okay, and you figure out the second point, right? And again, from there, he goes left to right. Right, so if you do that, right, so again, right, so at each point you ask him whether he wants to go to the left or to the right from the segment. So maybe it's kind of more productive to draw it sort of by growing a segment. So this here is, you know, the top. Now you know the second guy. Maybe the third guy is there. The fourth guy is there. So they are growing this contiguous segment of his, you grow this prefix of his vote, which is a contiguous segment of the axis, and you're asking whether you want to grow it left or right at each step, right? And that gives you 2m-1, right? And this is actually the algorithm from the original paper. So one actually doesn't need the factor of 2. You can actually do it with roughly m queries, I believe. Right. Yeah, so going from the endpoints in, right? Okay, so what do? You ask him to compare C1 or Cn. So instead of building his preference ranking from the top, which has the disadvantage that you have to figure out the top first, you build it from the bottom, and this is more convenient because for the bottom you really only just have 2 options. So you rank him, so you ask him about C1 and Cn, and effectively you're asking him whom do you hate more. Right, so you ask him to compare, but what you care about is whom he hates more, right? So he says Cn, so now you know that Cn is last, right? And inductively you ask him about the prefix of C1, Cn, right? So whom do you hate? So what is your most hated candidate out of C1 and Cn minus 1? So you build it from the bottom, right? And that you do in m-1 query. So it's really funny that the original paper, it's a paper by Vince-Konitzer, only points out the 2m-1 algorithm rather than kind of m-1 algorithm, but yeah, but this is what you have, right? So this is one reason we are writing survey on this kind of to clear up this kind of parts. Okay, so m queries. So can you really do better? So remember we had a counting argument, right? So we counted, okay, so we counted the dual thing. So we counted how many axes can there be for a single vote, 2 to the m, right? But the same question, it's effectively the same question as how many votes are there kind of that are single peaked with respect to a given axis, right? So these are dual questions, and it's 2 to the m, right? And you're trying to figure out which of the 2 to the m objects kind of you have to deal with, right? And because of that, you have to ask log of that, you have to ask m queries, right? So you cannot improve over that, this is tight. Okay, so that was single peaked with a known axis. Now let's talk about one Euclidean with a known embedding. So now imagine that these things here, so what you know here are positions of candidates, Euclidean coordinates, right? So this guy sits at 0.3, this guy sits at 1.2, this guy sits at 3.21, whatever, right? So these are Euclidean distances, right? So you know that, but you don't know the location of any voter. So now a voter comes in, and you don't care about the location of that voter, and you won't be able to get to that with just those queries. You're still asking the voter, you don't get to ask the voter about the location. You still ask the voter how he compares candidates, right? And you're trying to figure out his full preference ranking. But you have that as your supplementary information. So how many queries do you need to ask your voter now? Right, and actually, so the hint is you can do, okay, so of course it's single peaked, so you can do m, but you can do better than m. Binary search over what? Okay, so how do you, yeah, so binary search is the answer. So basically you need to know kind of where he comes in that picture. Well, so one thing to note is it's not enough just to know that he's between CR and CJ, because that doesn't fully determine all the distances, right? So it's binary search, but not quite on this space, on a slightly more refined space. So what do I need to do? Medians here. So you need half points. So how many half points do you have? Right. Well, you have half point between C1 and C2, but you also have half point between C1 and C3. Right. So you have, well, M choose 2 half points. Right. And these are the relevant points. The positions of the candidate themselves are not relevant. So the relevant points are those half points. Right. So you need to do the binary search on that space. Right. So how do you do binary search on that space? Okay, so these are, okay, so let me draw it again. So this is the midpoint, so let me write them as pairs. So this is midpoint of 1, 2, this is midpoint of 2, 5, this is midpoint of whatever, 6, 9, okay, so there's a bunch of them. So you pick, okay, so you pick some interval here. Or, okay, so you pick some midpoint. So basically what you can ask, so you pick the most central of these midpoints, right? So this midpoint, so there's M over, choose over 2 of them. So take M choose 2 over 2, take the central midpoint. And you want to ask if your voter is to the left or to the right of them, right? And you're asking if he's to the left or to the right of a certain midpoint, right? So that's asking him to compare 2 specific candidates, right? And once you get an answer, you eliminated half of your segment, so you're down to this half. So you continue to do that, right? So this is binary search on a space of kind of order m squared. So that costs you 2 log m, right? And note that how this is a very, very substantial saving even compared to single peaked. So knowing actual Euclidean coordinates helps you, well, effectively exponentially. You go down from m to log m, right? So this is huge. Okay, and this is also from the original paper by Konitzer on eliciting single peaked preferences. So this is actually hidden in the paper because Euclidean are not in the title, but he has a subsection showing that. Okay, so now suppose you actually have single crossing preferences, right? So then there are several flavors of the problem, but you can also do elicitation better than in the vanilla case when you don't know anything. So Neil, will you tell us about kind of one flavor of that of your choice? So whichever one you like.
Okay, so let's just do a very easy warm-up flavor and then just another one for fun. So when you have the single crossing profiles, they're essentially 2 high-level models. One in which you assume, okay, so one is the axis model. So one is what we call the random axis model, which is similar to what we've been doing so far, which is that you can ping any voter and ask them about any pair. Okay. And the other is the so-called sequential model, where think of votes as arriving in a stream in some order. And so voters come in, meet you, and then you can ask them whatever questions you want. And then you have to let go of them, and then you cannot query them again. Okay, so this is the sequential access model. So in the sequential access model, you probably already guessed that you can again have 2 varieties based on whether the sequential the sequence of the sequential axis coincides with the single crossing ordering of the voters or not, right? So the sequence in general can be arbitrary, but you could ask yourself if you can do better if you additionally know that the sequence in which the voters are arriving is the same as the single crossing sequence. Okay, so and indeed it turns out that you can do, I think, a little better in this case. But let's just think about the random access model, because that's what we've been doing so far. How many queries do you need to elicit the entire profile? So assume that you have a single crossing profile and you can ask any voter these pairwise comparison questions. What's a natural sort of strategy to follow? So I guess you can, yeah, let's assume that we know the ordering of the voters according to which it's single peak type. So maybe as a hint, I'll give you the target number of queries so you can reverse engineer what the process might be. So let's say I'm looking at roughly m choose to log n queries. This is to elicit the entire profile. So I'm not looking at it vote by vote because that's probably not as convenient in this case. For single peaked, often you just say this is what it takes to elicit one vote, and then you just multiply that by the number of voters for the total number of queries. But here it may be more convenient to think of it as really a bulk problem. So the log n should tell you something, I guess. Okay, binary search to find the crossing points. Okay, yes, good. So, no, this is still random access. So, yeah. So, we started with random access for the warm-up there. So, okay, binary search to find the crossing points. Anyone wants to come and elaborate on that, or?
So like for every pair we and voters, like where did the cross?
Right, exactly. So, right. So let's fix a pair of candidates A, B, and we can query the first voter and the last voter. Let's assume that the first voter says that she prefers A over B, and the last voter says that she prefers B to A. If they both coincide, of course, then you don't need to query any further because they all are unanimous on this pair. But otherwise, you know that one switch has happened. And the question is, where is that switch? And this is something you can find out by binary searching, right? So you ping the middle, and depending on who the middle guy is consistent with, you either move up or down to find the crossing point. Okay, and what happens at the end of this process? So we do this for every pair of candidates. So that's n choose 2 pairs, and it's log n plus 2 queries for every pair. And at this point, you basically know for every voter, you know their pairwise preferences between every pair of candidates. So, so that should lead you to the vote. So it's no problem. Okay, good. So let's do another sorting inspired elicitation algorithm. So let's say that you have the sequential setting. But with voters, This is a slightly easier case where the voters are arriving in the same order as the single crossing order. So So again, I should probably give you a target to work with, otherwise this can be a little weird. So the trivial elicitation algorithm, which works even when you don't know anything about the profile, takes mn log m queries, right? So that's essentially m log m to elicit one vote, and n is the number of voters, right? And in fact, in this setting, you can actually come up with a lower bound argument to show that m log m, in fact, so this is something I'll tell you without actually proving it, because the proof is just some messy details. But I think even this is unavoidable. Like, you do need m log m plus mn queries. Sorry? Yeah, so this is all asymptotic, so I'm not worried about the, maybe off by a factor of plus minus 1. So, right, so let's see. So what's our target? Our target is going to be see. So I don't know if these expressions are as clear as I'd like them to be, but essentially this is what you can do easily, right, without any effort. And you cannot do, I mean, you need at least these many queries, roughly, okay. And right now I'm just saying let's improve this to, so instead of the number of queries being log m times mn, saying let it be mn plus m square, which okay, yeah, I mean, which is an improvement when the number of candidates is kind of small. Yeah. Let me just make sure that I got the target right.
M square and the m log m portions
Mm-hmm.
are only relevant for the bootstrap case, that is the first one, right?
In some sense, yes. Not the m log m is for bootstrapping. That's right, and the n square is still going to be useful for you to get your overall bound. Yeah. So basically I'm saying that, well, you could try to come up with an algorithm that matches the lower bound. I just don't know how to do that. So I'm saying instead of paying a log m per m, I'm giving you more leeway and I'm allowing you to pay m per m. So m squared should be okay. Right. So okay, I just put these on the board to motivate the idea that this is a reasonable target to shoot for. So you don't have to actually, so this is no information and you don't have to worry about the lower bound, just believe me when I say that that is the case.
So at any point in between the sequential process, we would first of all need to know the profile in that because
Right.
right, the folks before have already gone.
Correct.
Right. So now
Unless, okay, I don't know how to make that statement formal. For single crossing, it's probably true. But in general, it's conceivable that you have a situation where the voters who come after actually give you some information about the voters who have already gone. Yeah. So.
yeah,
but okay, let's assume that this is true.
let us assume that we are.
Yeah, we are interested in.
ith step we construct the
Yeah. Yeah.
So if we know the I minus 1th vote, then we know that then to construct the ith vote, we essentially ask for every consecutive this thing. We ask
Right.
this still holds, and if it doesn't, we do that kind of like
Right.
bubble
Right.
sorting kind of
Yeah.
swaps.
Yeah. Right.
So therefore, the number of queries that we require would exactly be equal to m plus the swap distance of.
Right. Right. Okay. Yeah, that's a good point.
Since the swap distance is bounded by m square between
Right.
the first and last.
Right. Right. Yeah. That's essentially it. So you need the m log m to get the first voter's vote because that's crucial for starting of the process, right? So the first voter comes in and you query him completely, and you have the first vote. From there on, essentially, what you want to do is. So the intuition is what we have already seen when we did the swap distance exercises, that in a single crossing ordering, the consecutive votes are not all that much different from each other. Okay, so let me just repeat what was already said. So you have the first voter's vote completely, or it's just assume that this is C1 over C2. When the second voter comes in, I'm going to query him on the first pair, for instance, right? And let's just assume that the first voter goes along with the second voter is essentially identical on the first voter up to a certain point. And then let's say you start having, so at some stage, when I look at Ci and Ci plus 1, the second voter says that he actually doesn't agree and that I vote Ci plus 1 less than Ci. So then you'll have to make, then Ci plus 1 has to be basically queried with a bunch of people until you find the right place for Ci plus 1, right? And this is what you do. So this is essentially a lot like insertion sort, or you can think of it as bubble sort. So you're trying to fix. So for each I, you're trying to find the right place to where to place him, right? And if it was just, if you just stared at one voter in isolation, then the insertion process can take as many as m queries. And so if you just did a naive bound, then that would be m times n. But the key here is that as you pointed out, the total, so you can think of this as the number of queries that, the number of overhead queries that you have is essentially the swap distance. It's the number of pairs on which these guys differ. And the total swap distance between the first and the last word is m squared. So that's where you get your bound from. Right. Cool. All right. Okay, so there's like a bunch of other settings in which you could ask yourself the same questions. Sequential, but they're not necessarily coming in the same order as the single crossing order. And you could also ask yourself what's the best you can do when you don't know the single crossing order at all to begin with in both of these models. So, so it's a bunch of interesting elicitation questions. The lower bound questions are at least as interesting, coming up with examples that show that you do need at least a certain number of queries. So, so if you just want some food for thought, it's a nice puzzle to figure out. Lower bounds for both the easy case when we had random access and for this one. You had a question? Okay, cool. All right, so I think I'm done. Thanks.
So I have 2 questions left. So both are easy, and well, we are going slightly longer than we expected, but we also started later. So let me just go through them quickly. So I think the second one should be pretty obvious given what we have already seen about single crossing collections. Okay, so who wants to tell me the answer? Why are there at most order of m squared distinct votes? Distances, right? So they all have to be, so one way to see it is they all have to be at a distinct distance from the first vote. Right, so you fix the first vote, the distances are the number of pairwise comparisons, so this is order of m squared. So m choose 2, so can't be more than that. Can't be m choose 2. Right, so this is important because it really distinguishes single crossing profiles from single peaked profiles. Right, if you fix an axis, we just argued, so there can be 2 to the m different single peaked orders with respect to that axis. Right, but if you have but you can't have a long, so you can have a long single peaked profile, but you cannot have a long single crossing profile, not without repetitions. Right, so that's sort of another reason why you sort of, well, maybe see them in practice less often. Right, and finally I wanted to have a question about preference single peaked on a tree, just because this is also something we discussed and we haven't covered it in this tutorial. Right, and the point here is that if you have preferences single peaked on a tree, you are not guaranteed transitive majority preferences. Right, so in particular, so you can have a majority cycle. So majority prefers A to B, B to C, C to A. So importantly, right, so as we argued yesterday, there would still be at least a weak under 7, right? But you can actually have a proper majority cycle, not weak but proper. Strict majority prefers A to B, strict majority prefers B to C, strict majority prefers C to A, right? Okay, so how do we argue that? Well, the place, okay, so what makes tree different from a path? Well, the tree branches, right? So the tree branches non-trivial, right? And that seems like a good place to look for this bad cycle. So suppose your tree branches here, right? So these are alternatives around the branch, A, B, C, right? So you can have a voter, so suppose you have a voter whose peak is here. Right? So how can this voter rank A, B, and C? Arbitrarily. Right? So we don't restrict him in any way. So in particular, we can have 2 such voters that go A, B, C, 2 voters that go B, C, A, 2 voters that go C, A, B. Right? So they would all rank this center, let's call him D. They would all rank D first, right? But kind of for A, B, C, they can be arbitrary, so they can be a majority cycle. So in that sense, preferences single peaked on a tree are much less nice than preference single peaked on a line. So in particular, finding winning K-many ranking on a tree is hard because it can be a complete mess below the top. But okay, but at least you still have Cantor 7s. Okay, so that's the end of that tutorial. So I'm afraid we have 3 more hours in the afternoon. So hopefully we can get to that. So eat a good lunch. Right, so maybe something, something spicy or something caffeinated to keep you awake for those 3 hours. I'll certainly do that.